In this segment, we will introduce you to nonlinear regression just to give you an overview of what nonlinear regression is all about. So the nonlinear regression models work just like the linear regression models so far as the fundamentals are concerned. So we are given n data pairs right here. And what we want to be able to do is we want to best fit some function f to it, which will have the constants of the regression model in it. So let's suppose if f was a straight line, then it will be the intercept and the slope will be the two constants of the regression model. So it might look different, but it is the same way as we did our linear regression models. So the philosophy is still the same, is that we have these n data points which are given to us, and then if we try to draw a curve which best explains that particular data, there will be a difference between what is observed and what is predicted. This is the observed value, and this is what is predicted by the regression model. The difference between the two, this part here is called the residual. So your residual is y sub I minus f of x of I. Observed value minus predicted value. And what we want to do is we still want to do the same thing. We want to minimize the sum of the square of the residuals, and that'll be summation I is equal to 1 to n y sub I minus f of xi whole square. And so what that simply means is that we are taking each residual, squaring it, and then we're adding all of them up. And what do we want to do? We want to be able to minimize this SR with respect to what? With respect to the constants of the regression model of this function f. So as I was mentioning, that if it's a straight line, it'll be the intercept and the slope. And similarly, for the nonlinear regression models, you'll find out that it has similar kind of constants with respect to which you want to make SR to be as small. Let's look at some of the common regression models which are used in science and engineering. So one of them is the exponential model. So as you can really see here, there is that it has two constants of the regression model, A and B. So you are given data y is a function of x, and what you're doing here is that you are trying to regress this data to an exponential model. A good example of an exponential model is if you have heard of somebody getting a CT scan, let's suppose, because they want to figure out what's wrong with the person. So what they do is they give you a radioactive dye, and that radioactive dye goes into your body, and then they're able to, when they do the scanning, they're able to see that, hey, if there is something wrong with that particular person. But if you're going to put a radioactive dye in somebody's body, there is going to be a radiation intensity which is going to be in that person, and this radiation intensity is going to decrease as a function of time. And that decrease which is taking place with respect to time is given by an exponential model such as this one. So as time increases, you'll find the radiation intensity is exponentially decaying. And in order to be able to figure out that, if you want to figure out the regression model based on if somebody's measuring the radiation intensity as a function of time, and then you want to regress it to a exponential model, that's the one which you would use based on the physics of the problem. Let's look at another nonlinear regression model. It's called the power model. And here what we have again, A and B are the two constants of the regression model. A good example of that is that you might have seen a parachutist sometimes, and the parachutist has a parachute which is using in order to come down safely. And then you can very well see that on this particular parachute, there's going to be a drag force. So this drag force which we have here, drag force, it is going to be given by some constant c times v raised power b, where this v is simply the velocity with which the parachutist is falling down. So you can very well see that if somebody is giving you the data of drag force as a function of velocity at different points, then you can calculate what these constants of the regression model are. So for example, this is a measure of the drag coefficient of the parachute. Let's look at this another example here of a nonlinear regression model. It's called the saturation growth model. The reason why it's called saturation growth model is because at x equals 0, you find y is 0. but the reason why it's called saturation is because as x approaches infinity, y approaches a. And you can see that just by doing some calculations or by just some manipulation here. If I divide by x both the numerator as well as the denominator, I will get a divided by b by x plus 1. And you can see that as x approaches infinity, the y will approach this value a. So that's like the saturation growth model. And the way it looks like is something like this. If this is y and this is x, and these are the data points for the saturation growth model, it'll look like this. So it's eventually going to saturate. It's going to start at 0, and eventually it's going to saturate to a constant value, which will be a. A good example of this one is something called, I'm sure that you have seen an animated picture in your life. And if you look at if you try to plot the performance, let's suppose we can measure it by how good does the animation look. So that can be a measure of performance. And then on this side, on the x-axis, can be the frame rate. Frame rate meaning that how many frames are being used per second. So if you are using many frames per second, you're going to find out that you're going to get a better performance. Performance meaning that, hey, how does it look? You must have seen some of the movies which have been made lately, animation movies. You find that they are almost as good as real life and in real life movies. But at the same time, that if we increase the frame rate too much, we may not get any more performance from there, any more big change in the performance. So you want to keep the frame rate to be at a certain percentage of the maximum performance you might expect, which would be, let's suppose, at 100%. And you don't want to use very high frame rate because that costs money, that costs computational time. So you want to come up with a frame rate which will be the best one for a particular scene. So in this case, you'll have a saturation growth model. The performance is 0 when there is no frames being shown to you, right? But as the frame rate increases, more and more frames are shown per second, you will find out that the performance of the animation which you will see turns out to be a good one. So that's the nonlinear regression. So let's go back to the exponential model and just repeat what we saw for the general regression model. The reason why we do that is because in the general regression model, we use a function called f of x. And then people say, hey, what are the constants of the regression model? So here they are for an exponential model right here, a and b. So all we are doing is that given the n data points which we have here, we want to be able to find the difference between what is the observed value and what is the predicted value. So your observed value is y sub I, and your predicted value be a to the power bxi. And what you want to do is you want to again do the same thing as we did for linear regression. We want to take each of the residuals, we want to square it, and then what we want to do is we want to add all of them together. So this will be a e to the power bxi. And we want to add all of these residuals, so the square of the residuals, and we get the sum of the square of the residuals. What do we want to do now? We want to minimize with respect to a, and we want to minimize with respect to b, so that we can find out what these constants of a and b are. And that's something which we'll do in the next lesson. And that is, of course, the end of this segment.